afternoon. How's everybody doing? Yeah? Come on, you can do better than that. Come on. How's everybody doing? Brilliant. All right. I realise that it's basically nothing between you and a cold drink except for this talk. So we'll try and get through lots of information in quite a short space of time. How many of you today have already seen one or more talks that talked about eBPF? I know there have been a few. Right, good. Okay. And how many of you feel like you've got a pretty good idea what eBPF is? Anybody feeling like they're pretty confident? Good. Hopefully this will reinforce that and tell you some more about how eBPF is being used, particularly for security. I am going to kind of start at the beginning of the story just to make sure everybody's on the same page, but we'll try and get through the beginner stuff pretty fast. I realised I didn't introduce myself. My name's Liz Rice. I am Chief Open Source Officer at Isovalent, which I'm sure you have probably all heard today is the company that originally created the Cilium project. We're also very involved in and well, one of the sort of creators of eBPF. I joined Isovalent because it's just full of people who know so much about eBPF, and I've learned a ton since being there. It's something I've been fascinated by for quite a few years now. I just love being able to be immersed in it. And I've also been pretty involved in security for a while. So this kind of intersection of eBPF and security is pretty much my sweet spot. So you all know that eBPF allows us to dynamically program the kernel. We can change the way the kernel behaves on the fly. And let's just pause for a second and make sure everybody's on the same page about what we mean when we say the kernel. The kernel is the bit of the operating system that coordinates with hardware. It interfaces to any hardware. If you're writing an application in user space, you can't access hardware directly. You have to use system calls to ask the kernel to do it on your behalf. So whenever you're accessing a file or communicating over the network or accessing memory, that's all going to involve the kernel. The kernel is also coordinating multiple different processes at the same time and looking after things like capabilities and permissions. So the kernel is involved in pretty much anything interesting that's happening on a machine. And with eBPF, we can attach custom programs to events, arbitrary events, pretty much anything that's happening on the machine. We can attach an eBPF program to that event and do something interesting. Things like accessing files and sending network messages and changing privileges and reading and writing to memory are all the kinds of things that are interesting from a security perspective. We might want to look at those events and see whether or not they are legitimate or potentially malicious. But before we get into talking about how we're using eBPF specifically for security, let's just sort of rewind and think about some of the basics. Has anybody already done like a Hello World demo today? Okay, I'm gonna do one just to sort of make sure. So this is a very simple, I should make this hello KCD Zurich, shouldn't I? This bit here is my BPF program that I'm going to load into the kernel, and everything else is sort of user space stuff that's loading it into the kernel and emitting events. So if I run that, and I need to be root to do it, okay, and because I'm using a VS Code remote machine, there's actually loads going on this virtual machine, so that's being triggered quite a lot, as you can see. And if I were to run something else on that machine and quickly try and catch it, we can see process ID 6951. We caught an event that was triggered by a bash executable with process ID 6951. So we can attach to events, we can collect information about them, things like what process is involved, what executables involved, all that kind of information is accessible to our eBPF program. If we were looking at a network event, we would have access to the network packet. We have this contextual information whenever we're running an eBPF program. eBPF has been used to instrument pretty much every aspect of a running system. There's a collection of tools in the IOVisor project that this diagram kind of shows what the collection is. Don't worry about all the details. I know it's kind of an intimidating diagram. There's a lot going on here. But really the point is you can, or somebody has already, written eBPF tools to instrument and detect what's happening in pretty much everything that's happening on a machine, whether it's to do with files or memory or networking or user-space applications. We can instrument all these things with eBPF. One example would be OpenSnoop, which we can use to observe whenever files are being opened. So I've got that also available here, I'm pretty sure. Here we go. OpenSnoop, again, there's a lot going on this virtual machine, and we can see lots of files being opened. So that's all well and good. How do we use that information in a cloud-native environment? What does it mean to use eBPF when we're in a Kubernetes environment? We're running our applications in containers, and those containers are in pods. But however many pods we've got, however many containers we've got, they're all sharing one kernel. There's only one kernel per virtual machine or bare metal machine. And that kernel is involved whenever those applications are doing anything interesting that touches hardware. So whenever any of our Kubernetes applications are sending network messages or accessing files, or whenever Kubernetes is creating new containers, the kernel on that machine is involved. And that means we can instrument that one kernel and see what's happening across all of the pods, all of the applications that are running on that node. And we don't need to change anything about those applications. We can load the program dynamically into the kernel, and it immediately starts seeing events. When I started running OpenSnoop, you could see lots of processes were opening files. I didn't have to change those applications for OpenSnoop to see them. Because it's running in the kernel, an eBPF-based tool will automatically get visibility into things that are already running. So this makes eBPF a really powerful platform for building observability tools, and then from there, security. One of the things we need, though, in a Kubernetes environment is contextual information about Kubernetes. So when I showed you OpenSnoop, in fact, let's go back to it, we can see things like process IDs and executable names. We're probably seeing things like exit codes here. We're seeing the name of the file being opened. But this wouldn't give us Kubernetes information. In a Kubernetes environment, we want to see things like what node it was running on, what pod, what namespace. How do we get information about individual pods and individual applications on that Kubernetes node? And the answer to that is pretty complicated because there are no kernel constructs that relate to Kubernetes. This involves quite hard work on the part of eBPF developers to figure out how a process relates to a particular pod and all the kind of Kubernetes context that it relates to. But fortunately, that work has been done so that you don't have to. So for example, Cilium is connecting pods in Kubernetes environment, and it has all that contextual information about what those pods are, what namespaces they are, what services they are offering, all that kind of thing. Another example is Inspector Gadget. And this is quite a nice tool that you can install. Runs a variety of different tools that are based on those IOVisor, you know, that complicated diagram with loads of different tools. Quite a lot of those have been ported to Inspector Gadget. And this example is showing basically OpenSnoop, but with additional Kubernetes information added to the output. Other examples of observability tools, or getting information that has this Kubernetes contextual information, would be the Hubble component of Cilium. How many of you here are using Cilium? Few hands. How many of you are aware of Cilium? Have you seen some talks about it today? Great, excellent. So Hubble is the observability component. So you can run Cilium without Hubble, but you're probably going to want to run Hubble because it will show you all sorts of information about networking in a Kubernetes cluster, such as how are your services connected, which services are talking to which other services. You can see individual network packets flowing. You'd be able to see if they were being blocked by network policy. And Hubble also generates Prometheus metrics, which we can then use to generate all kinds of really interesting dashboards, all sorts of interesting graphs, maybe on Grafana, for example, things like latency or throughput, or how many error responses we're getting to messages, or how many packets are being dropped. So tons of information being collected using eBPF with all that contextual Kubernetes goodness. So far I've talked about observability, so how does that relate to security? When we talk about observability, we're really saying we're collecting information about events that are happening on the system, and we might use different formats of information, but we're using that information to answer questions. How is my system behaving? What's happening on my system? The difference between this and security observability would really be policy. So we wouldn't just be saying, show me what's happening. We'd be saying, compare what's happening to a policy. The policy says what I consider to be legitimate or illegitimate. The policy says what events, what criteria I'm looking for that maybe indicate malicious behavior. And then if we detect some malicious behavior or potentially malicious behavior, we want all that contextual information so we can say, well, what pods were affected, and can I figure out how this security event occurred? Has something been compromised? Is some unexpected executable running? So eBPF is a really great tool to generate those initial events. And then the question comes, how do we compare those events to policy? As I said before, we're really interested in events that are happening in the kernel. That's a really great place to find security-relevant events. Now, one kind of natural place to build security tools is often that syscall interface. So a lot of the sort of first eBPF-based security tools thought, well, OK, I've got applications in user space. Maybe some of those applications are behaving badly. Maybe they've been compromised. Somebody has run a malicious executable on my node. It's still running in user space. So if I can observe what it's doing, perhaps observing the system call interface, I can use that to detect security-relevant events. And the natural sort of place to start thinking about that is that system call interface. There is a problem with this, which is when you make a system call, you're passing information, some parameters from user space to kernel space. And user space and kernel have different memory. They use different parts of memory. And when you make the system call, information that you currently have in user space memory needs to get copied into the kernel, and the kernel will build up some data structures about what it is that you want to do. So imagine, for example, you're trying to open a file. There's a system call for opening a file. There's probably a pointer to the file name that you want to open as a parameter. That's one of the parameters. That's going to get copied into kernel memory. But there is a window of opportunity for an attacker to change what that memory is pointing to between the point where user space makes the call and the point where the kernel actually acts acts on the information. This was really well discussed in Cloud Native Day a couple of years ago, Cloud Native eBPF Day, and explored in a DEF CON. It's kind of interesting because all these security tools had been built using this interface. But if you go and look at the kernel documentation, it kind of says, do not use this for a security tool because it's really not secure. So there were clues in the documentation. So what we need to do is make security checks after the kernel has copied those parameters copied things from user space memory into kernel memory. I'm going to say that there are plenty of reasons or plenty of times when it's fine. If you're basically doing observability, it's totally fine to observe system calls. It's really if you want a proper security tool that you want to be conscious of this vulnerability and the possibility that if you're building serious security tooling, you should not base it on something that is documented as not a security interface. So, the place in the kernel, or a place in the kernel, that is sort of officially used to provide this checkpoint after parameters have been copied is called the Linux Security Module API. Now, this is a stable interface inside Linux. Has anybody here used SE Linux or AppArmor? Yep, quite a few hands. Keep your hand up if you enjoyed it. Okay. So both those tools are using this LSM API to get information about the events that they're policing. It's a stable interface. It's designed for security. It's your application on the other side of the interface is being given the kernel's representation of these data structures. So it's a safe place to make these security checks. So it's a great place to run eBPF programs that can be much more dynamic and much more kind of customized to the security checks you want to make. So for example, rather than having those very kind of fixed ways of configuring tools like SE Linux or AppArmor, you can load eBPF programs that can have very bespoke, custom criteria that they're looking for. Plus, you can use eBPF dynamically. It's going to protect any pre-existing processes. It's a great potential interface for security tooling. And there had to be changes made in the kernel to allow BPF programs to hook into these sort of LSM interface. But they're really useful. It's a great place to run BPF programs because you've got access to information like the file name after it's been copied into kernel memory. I've got a little demo of this as well, actually. So I've got a eBPF program here. I've actually got two eBPF programs. One is attached to the system call, and it's a system call for chmod, changing the permissions on a file. And that's just going to tell us that the system call was triggered. But I've also got another program here that I'm attaching to that LSM interface. There's a hook on that LSM interface for chmod, and it comes with a path structure. This is a kernel data structure from which we can get the file name. So if I run this program, and I also need to, I think that's already running, looking at the trace output. And then if I think I've got a file, have I already got a file called Liz? Yes, I have. So if I try to change the permissions on that file, we trigger both of those eBPF programs. One of them was just the system call, but we can also see the name of the file got included. And if I can show you the code again so you can see I didn't hard code that. Wouldn't cheat. All right. So this is great. This could be a really fantastic basis for building security tools. Except those changes were put into the kernel in 5.7. I doubt many of you are currently running 5.7 in production. You might be, but a lot of you won't be. Most distributions are not using such a modern kernel yet. This is one of the reasons why eBPF is so useful, because changes in the kernel typically take maybe up to 5 years to really get used in production by hardened Linux distributions. So although this is a great idea, you might not be able to use it yet because your Linux distribution might not support it. It also needs to be said, somebody has to do some work to add Kubernetes context. You don't automatically get any Kubernetes context information here. It requires kernel knowledge, eBPF programmers to understand how to get that contextual information or convert from process IDs to things like the Kubernetes pod and the namespace and what have you. Could we do that? Well, although the LSM API is a stable interface and it's guaranteed not to change, that's one of the reasons why you would use that set of BPF hooks. But like I said at the beginning, you can hook into pretty much anywhere. You can hook into any event on the kernel. You can hook into almost any function call in the kernel. Some of those functions will change from one release to the next. So if you wrote a BPF program that relied on a particular function, next Linux release, it might have changed. But loads of functions haven't changed for years. Loads of things about Linux are really pretty stable. They're not officially stable, but in practice, they're stable. And folks working on Cilium, a lot of them are kernel engineers who know how stable a lot of the kernel is. If it was going to change, they would be involved in changing it. So they've kind of got this knowledge about what are sufficiently stable areas of the kernel where we can take a punt that those aren't going to change in the near future. So we have this tool called Tetragon that's part of Cilium. Who's heard of Tetragon before? Anyone? Actually, loads of you. Excellent. So Tetragon is using this kernel knowledge to work on older kernels that don't yet support the LSM API. And it's using Cilium knowledge about how to extract the Kubernetes contextual information. It got called Tetragon because it's named after a Tetragonisca angustula bee. This is a small bee. It apparently produces lots of honey. It's considered harmless to humans. It builds unobtrusive nests. I think all of these are very good metaphors for small programs that produce large amounts of useful information while not requiring very many resources. And that's kind of what Tetragon is. So Tetragon's going to have a policy, talked about security policies, that's going to define what kind of events we're interested in and observe events. Those events might be, defined by the policy. If we have a policy like this, for example, that says, I'm only interested in knowing about changes to or file access events in the etc. directory, that's being filtered in the kernel, which is great. We don't have to look at every single file open event and then filter it in user space. We can actually filter it within the eBPF program. So we only need to send user space events for the events we're interested in, the events that match the policy. So by default, we always get process starting and exiting events. And then you can see here a series of events that relate to a file being accessed in the etc. directory. We've also got the Kubernetes information. So we've got the namespace and the pod name. There's actually a ton more information in the non-compact version of this output. Now, imagine if you can combine that with the network information as well. So we've got information about process execution, file access. If we can look at the tree of processes so we can see what processes are running in which different pods. We can see when network access is being triggered. A lot of these network access examples look fine. I mean, well, maybe accessing the Twitter API isn't such a good idea anymore, but, the one I'd be really suspicious about is this last one. Something not reverse shell looks very suspicious. So if you have this information about what was the process that generated that connection event, what executable was running, what pod was it running in, when was that pod started, all this kind of information is really useful for forensics to understand how a security suspicious event has taken place. So the last thing that we might want to think about if we're talking about security is, can we not just observe these events? Can we stop them from happening? Well, we do this all the time, right? We do network security events preventatively all the time. So network policy, in Cilium, we enforce network policy by dropping packets with eBPF programs. We've done this kind of thing, dropping packets with firewalls for years. This is not sort of a new concept. So in the networking world, we are very used to this idea of preventing bad things from happening. We take action to drop packets that look suspicious. Can we do the same thing for suspicious-looking runtime events? There certainly are lots of tools that will try to do that. So the kind of traditional way to detect this is, or to create preventative actions, is we detect something doesn't meet the policy, something looks suspicious, it looks like it might be an exploit. The kernel probe, the eBPF program, spots this suspicious event and tells some kind of user space rule engine. In fact, quite often it's going to be spotting an event, and the user space rule engine is the thing that's going to decide whether it matches the policy or not. And then the user space rule engine might say, well, this looks suspicious, so maybe I could kill the application or the process that generated this dodgy-looking event. The problem is, while that is happening, while the kernel is notifying user space, bad things could happen. Data could be exfiltrated. You haven't prevented something from happening. What we can do in Tetragon is actually send the signal directly from within the kernel so that it's synchronous. There's no opportunity for bad things to happen before the user space rule engine would stop that activity. So that would look something like this. Let's see. I've got a few pods running in this kind of the Star Wars-y type pods running here. And let's just see whether I've got a tracing policy applied already. I do have a tracing policy applied. And hopefully the tracing policy is this one. It's called etc. password, and it's basically interested in etc. password. Don't worry about the details here. The most important thing is that if it sees a write, if a write operation happens, it's going to send that kill signal. So, where's my output from? There's my Tetragon output. So if I exec into, let's exec into an X-wing. And Tetragon should immediately start generating some events. So we can see my bash executable was started. As part of running bash, it checked the etc. password file. So we've already seen an open and a close on that file we're interested in. What happens if I try and look at the contents of that file? Yeah, we can see it got opened, it got closed, my cat executable terminated, that's fine. What if I were a bad person and I wanted to compromise the X-wing and I wanted to edit the password file? Okay, We can see it's been opened. Weirdly, Vi sort of opens and closes, but yeah, whatever. So if I tried to do bad things in this file, hopefully, yeah, it got killed. Did my bad things take effect? Let's take a look at the file again. Oh, it scrolled off the top. That's, that's not great. Can't see the top. Yeah, no, so now you can see the top. My bad things did not get written into that file. So we were able to prevent an obviously malicious activity from taking place by killing that process. We didn't have to kill the whole pod. We just killed that process. So I hope that what that shows is eBPF is a really powerful tool for instrumenting applications. We can instrument things dynamically. We don't have to change applications in any way. We can get Kubernetes information because eBPF developers have spent a lot of time figuring out how to extract it. And that can be used to build incredibly useful tools for diagnosing issues and even preventing security issues. If you find this kind of information interesting, let me tell you about a couple of events. So there is a security summer school happening online, so check that out on the Observability website. Also, I don't know if any of you saw Bill's talk earlier today. I know he mentioned the eBPF Summit. The website is now live. This is new news. You can sign up and register or submit a talk to the eBPF Summit, which will be online in September. And if you would like more information, I hope some of you already picked up a book earlier today. There's still a few more What is eBPF books at the Observability booth, so do drop by and get those. You can also download electronic copies of all three of these books from the Observability website. I know I kind of ran over a little tiny bit on time, but if there are any questions, I'm happy to take them. Let's see how that goes. Thank you so much. Who's got a question? Somebody must have a question.
Everybody's thirsty.
That makes sense. Yeah. Maybe that is the question. Where is the beer? Yeah. You can always come and find me after as well and ask me questions if you want to there. It's the end of a long day. Okay. All right. Thank you.